Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are undertaking a critical deep dive into, really, the foundation of any successful construction or machine design. We're talking about the principles of strength of materials and, just as important, engineering material selection.
This is it. This is the knowledge that turns all those abstract concepts from a materials data sheet, all those numbers like CI, pounds per square inch, into a real practical structure, something you can actually guarantee will not fail.
Right, so our mission here is to understand not just what a material is, but how it behaves.
Exactly. How it behaves when you apply external forces, whether they're static, dynamic, or cyclic, and what happens when it deforms.
Okay, let's start where every good design process has to begin, with the vocabulary.
Hmm.
The language of force and change. We're talking about stress and strain. Now, we know stress is that internal force per unit area, but let's quickly clarify strain, because that's the fundamental measure of deformation, isn't it?
It is. Strain is, it's simply the measure of dimensional change relative to its original size. It's a unit of deformation.
So it's a ratio.
It's a ratio. If you're stretching a component, you just take the total length it changed by, and you divide that by its initial original length. So for instance, if you stretch a 6-inch bar by, say, 1/4 of an inch, the strain is just 0.25 divided by 6, which gives you about 0.042 per inch. You're looking at relative movement, not the absolute change.
And the beauty of most engineering materials, at least early on, is that this relationship is wonderfully linear, all thanks to Hooke's law.
Precisely. Hooke's law tells us that up to a certain point, we call it the proportional limit, the body deforms in direct proportion to the unit stress you put on it. That linearity is what makes predictable design even possible. You can see it perfectly in a simple mechanical spring.
And when we quantify that specific linearity, we get the material's fingerprint of stiffness, the modulus of elasticity, or what most people call Young's modulus.
Young's modulus, yeah. It's the ratio of unit stress to unit strain, but only within that proportional zone. A high modulus means the material is incredibly stiff. It takes immense stress to get a tiny amount of strain.
And a low modulus means it's more pliable.
Right. It basically defines the material's resistance to elastic deformation.
But I mean, designers spend most of their time thinking about what happens after that linear zone. That's where things get dangerous, where the material stops being predictable.
That brings us to the elastic limit. This is the absolute maximum stress a material can handle and still
Snap back to its original shape.
exactly, and still fully return to its original dimensions once you remove the load. For a lot of steels, we often just treat this as the same as the proportional limit. But the truly critical number for structural integrity is the yield strength.
So why is yield strength so much more important than, say, the ultimate breakpoint?
Because yield strength is the maximum stress you can apply without causing permanent deformation. Think about it. If your bridge or your machine housing permanently bends, even a little, it has failed.
Even if it didn't snap in two.
Right. That permanent strain means your dimensional tolerances are gone, functionality is compromised, and the structure is now fundamentally weaker. It's over.
I find it really interesting that for materials that don't have a nice, clean yield point like some alloys or plastics, we've had to sort of invent one.
We use what's called the yield strength by offset method. It's just a standard way to draw a line on the stress-strain curve, usually offset by a tiny percentage of strain. And that line defines the boundary where we say permanent deformation has officially begun.
Now, everyone knows ultimate strength, the tensile strength. That's the biggest number on the chart, the absolute maximum stress the material can take before it just fractures.
Right, it's the very peak of the curve. But like you said, if you're designing against failure, you design against yield. If you hit the ultimate strength, it's already far, far too late.
Let's shift gears just a little. Let's look at a couple pairs of material properties that define how we can actually use them.
Yeah.
First up, elasticity versus resilience.
So we covered elasticity, that's the ability to snap back. Resilience, though, is a measure of the energy stored in the material while it's deforming. More importantly, it's the recoverable strain energy when the load is removed.
Okay, so like a bumper on a car.
A perfect example. You want it to absorb impact energy, deform, and then spring back without any permanent damage. That is resilience in action.
And for manufacturing, we have ductility and malleability. They sound similar, but they're not.
They both relate to formability, sure, but in totally different ways. Ductility is the ability to be drawn out into a long, thin wire. Think of copper power lines. Malleability, on the other hand, is the ability to be compressed or hammered or rolled into a thin sheet, like stamping out car doors or making aluminum foil.
Okay, let's connect this to our next segment, designing for real-world failures. Because in the real world, you never, ever design a part to operate right up to its yield strength. You build in a factor of safety.
The factor of safety, or FS, is a non-negotiable mechanism to minimize risk. Historically, you'd take the yield strength, let's call it S1, and you divide it by your chosen factor of safety, FS, to get your allowable working stress, S.
It gives you a buffer.
A comfortable buffer. Although modern practice often defers to allowable design stresses that are already set by authorities like ASTM or AISC, it standardizes that risk tolerance across an entire industry.
Now, the forces we deal with aren't always simple. Sometimes time itself is the enemy, which leads to some really interesting failure modes. Let's start with cold flow.
Cold flow is a major headache. It's the gradual, permanent deformation of materials that aren't very elastic. We're talking about things like lead or certain plastics like Teflon. They're under a constant static load and they just slowly squeeze out of the way.
So if I use a Teflon gasket in a flange, what's going to happen over a few months?
That constant pressure will cause the Teflon to gradually creep or extrude out of the joint and you'll lose your seal. If you're designing with these materials, you absolutely have to compensate, usually with spring loading or something that maintains continuous pressure as the material deforms.
Okay, so if a static load is one silent killer, repeated, varying loads are another, this is fatigue.
Fatigue failure is a really complex phenomenon. It's caused by cyclical loading. Think of a rotating shaft or an airplane wing flexing over and over, and even if the stress never gets close to the yield strength, these microscopic cracks can form.
And they just grow over time until
Until catastrophic failure. What's crucial here is understanding the fatigue endurance limit. This is the highest unit stress you can apply repeatedly, indefinitely, without causing failure.
And that limit depends hugely on the material and how it's treated.
Oh, absolutely. For example, a medium carbon steel with a Brinell hardness between 150 and 200 might have an endurance limit somewhere between 42,000 and 50,000 size. Keep your operating stress below that, and in theory, the part should never fail from fatigue.
And there's also stress rupture failure.
Right, that's common in some high-performance aluminum alloys. The material's allowable ultimate strength actually goes down the longer a high load is applied. Time literally eats away at its strength.
Let's pivot to the really dynamic stuff.
Yeah.
Impact and shock. If a heavy object hits a structure, that kinetic energy has to go somewhere. Where does it go?
It gets dissipated through three main channels: deformation of the moving mass itself, deformation of the structure it hits, and conversion into heat. But what's truly surprising for most designers is the effect of a suddenly applied load, even if it's not a true high-velocity impact.
This is the key insight, isn't it? Tell us why applying a load quickly is so much worse than applying it slowly.
The data is clear. If you apply a load suddenly, and by that I mean almost instantaneously, but without initial velocity, that load produces stress and deflection that is twice as great as the same exact load applied slowly.
Twice the stress and twice the deflection. That's huge. And that's why we need tests that measure toughness under those conditions, like the IZOD impact test.
Precisely. The IZOD test uses a weighted pendulum that swings down and smacks a carefully notched specimen. The energy it takes to fracture that specimen, measured in foot-pounds or newton-meters, gives you a real number for its ability to absorb shock.
All right, moving on. Let's apply these concepts structurally. Let's talk beams and connections. When we analyze a beam, the first thing is always calculating the forces at the supports, which comes down to equilibrium.
Right. Two fundamental rules for any static beam. First, the sum of all your vertical forces has to be zero. Up forces have to balance the down forces. Second, and this is the core of stability, the sum of the moments of all those vertical forces must also equal zero. If the moments don't balance, the whole thing rotates and collapses.
And once we have those reaction forces, we can map the internal bending moment along the beam. And that immediately reveals the structure's weak point.
We call that the dangerous section. It's the cross-section of the beam where that bending moment is at its absolute maximum.
So for a simple beam with a load spread evenly across it, that's right in the middle.
Exactly. But for a cantilever beam, one that's fixed at only one end, the moment is always, always greatest right at the fixed support.
And we know the ultimate strength of a beam is tied directly to its geometry, its shape.
It absolutely is. The formulas link the ultimate bending moment M to the ultimate tensile strength of the material, Ft, and the beam's section modulus, S. For an I-beam, M is equal to Ft times S. but for a square section, it's 1.5 times Ft times S.
A 50% increase just for the shape.
And for a solid circular section, it's 1.7 times Ft times S. The geometry dictates a scaling factor for its strength. It's not just about the material.
We also have parts that handle twisting instead of bending, like drive shafts. That's torsion.
Right. When a member transmits torque, it's all about shear stress. We calculate the ultimate torque, TU, using the ultimate shear strength, FS, and a torsion constant, TC, which depends on if the shaft is solid or hollow. The goal is just to make sure the maximum shear stress from that torque stays well below the material's shear yield strength.
Okay, let's tackle what might be the most complex analysis here. Eccentrically loaded shear joints. You've got a plate held on by a bunch of bolts, but the load is applied off-center. This is a classic recipe for failure, because the bolts don't share the load equally.
It's a huge challenge. That uneven loading can cause just one or two fasteners to take almost all the load. And to analyze it right, you have to follow a critical 5-step process. It all starts with the geometry.
So why is step 1, locating the centroid of the bolt pattern, so foundational?
Because the centroid is the geometric center point. It's the point that the entire group of bolts wants to rotate around when that off-center load is applied. If you don't calculate your forces relative to that rotational center, your whole analysis is just wrong.
Okay, so once we have the center, what are the two main forces we're trying to combine?
You've got the primary shear force, which is just the main load divided equally among all the bolts acting straight down. Then you have the reaction moment force, Fn, created by that twisting action. It acts perpendicular to a line drawn from the centroid to each specific fastener.
And that leads us to the most critical step, step 4.
That's where you have to combine those two forces vectorially. You have to add the primary shear and the reaction moment force to find the true resultant force, Fr, on each bolt. They're almost never aligned, so you have to use trigonometry. The fastener with the highest resultant force is your weak link. That's the one that will fail first.
And step 5 is the final check.
Computing the actual shear stress, tau, on that most loaded fastener, you just divide that resultant force, Fr, by the cross-sectional area of the fastener, An. If that stress is higher than what's allowable for the material, the design is unsafe, period.
This is so important. That analysis could show that the bolts on one side of a joint are carrying 10 times the load of the bolts on the other. You have to know where that critical point is.
Exactly. It turns what seems like complex physics into a predictable way to avoid failure.
For our final segment, let's move into material selection, starting with the massive world of steel and the ASI designation system. That code gives you instant clues.
The ASI system is designed to give you immediate design information, mainly based on carbon content. If you see a low-carbon steel, say ASI 1006 to 1015, you know it's going to be highly formable, easy to weld, and perfect for things like sheet metal, where ductility is key.
And as we add more carbon,
We add strength and hardness, but we usually sacrifice some weldability and ductility. Medium carbon steels like 1030 to 1052, those are the workhorses for automotive parts and forgings. They can be hardened. Then you jump to high carbon steels, 1055 to 1095. You basically give up on welding them, but you get incredible wear characteristics, perfect for springs and tools.
the power of selection really hits home when you compare a basic plate steel to a highly treated alloy.
The difference is just staggering. Take a common structural quality plate steel like ASTM A36. Its yield strength is around, 36 to 38,000 CSI? Now, take a high carbon steel, ASI 1095, but instead of using it as is, you put it through a water quench heat treatment. That process boosts its yield strength all the way up to 138,000 CSI. The heat treatment completely transforms its capabilities.
For the engineer in the field, we have some neat identification tricks. Let's talk about the copper sulfate test.
Yeah, this is a great quick check. It's a fast way to tell plain steel from stainless steel. You put a drop of copper sulfate solution on a clean spot. If it's regular carbon steel or iron, a metallic copper film immediately forms on the surface. If it's stainless steel, nothing happens, no copper deposit.
And we can even tell different types of stainless steel apart with just a magnet.
That's the second trick. The common 300 series stainless steels, the austenitic grades, they're non-magnetic. But the high-strength, heat-treatable 400 series, the martensitic grades, they are magnetic.
And what about measuring hardness? The Brinell test.
Right. The Brinell hardness test works by pressing a hardened steel ball of a known size, usually 10 millimeters, into the surface with a very specific load. You then measure the diameter of the little circular impression it leaves behind. The smaller the impression, the harder the material. It's a direct, quantifiable measure.
Let's shift away from steels for a moment. Aluminum alloys are just indispensable today.
They offer an incredible strength-to-weight ratio. Modern aluminum alloys are strong, but they weigh about 2.8 times less than steel. That's why they dominate aerospace, high-speed rail, performance cars, anywhere that saving mass is critical.
And finally, let's touch on engineering plastics, where selection is driven by very specific functions.
Oh, the properties are extremely specialized here. Take polycarbonate, brand name Lexan. Its whole deal is being virtually unbreakable and optically clear. Perfect for safety shields, housings, things like that.
Then you have plastics for mechanical parts, for movement.
Like acetyl, which you might know as Delrin or Silken. This stuff has a high modulus and a ridiculously low coefficient of friction. That's why you see it used for precision bearings and gears.
And we come full circle back to failure modes with Teflon, or PTFE. It's a perfect case study in trade-offs.
Teflon is a miracle material in some ways. Unmatched chemical resistance, super low friction, great insulator, but
You have to remember cold flow.
you absolutely must apply that lesson. Because Teflon has essentially zero elasticity, any constant pressure will cause it to creep and deform over time. If you design a Teflon seal without accounting for that creep, your otherwise perfect design will fail. It's just a matter of when.
So we've covered the whole cycle, from fundamental limits, like Young's modulus and yield strength, to the complex analysis of off-center joints, and finally, to the specific quirks of materials like quench steel and PTFE.
When you connect all the dots, successful mechanical design is really about integrating these different domains. You have to pick a material that can handle the specific type of load static, dynamic, cyclic, and then you have to do the structural analysis to make sure the geometry distributes those stresses safely. It's not about finding the strongest material. It's about finding the most appropriate one that meets all the constraints without failing.
So what does this all mean for you? Well, the next time you pick up some piece of hardware, maybe it's a complex plastic housing or a lightweight aluminum bike frame, don't just see its shape. Think about the invisible forces governing its survival. Consider what property like its ultimate shear strength, or maybe Poisson's ratio, which dictates how much it shrinks sideways when you stretch it, governs the flex and durability of that seemingly simple object you use every day.
Understanding those intrinsic properties is how you move from just building something to truly engineering it for the long term.
This has been a true deep dive into the fundamentals of material integrity. And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together, stays together.